So nice, and again, welcome you all once again for continue of this lecture. So now we are going to discuss about how to find out concentrating collectors efficiency factor and collector heat removal factor. So how these efficiency factors will be defined and what is the purpose of collector heat removal factor, we will discuss here after mathematical analysis of these two parameters. So let us first define what is a schematic of the collector, concentrating collector dimensions. You see here collector cylindrical. We are taking example of cylindrical parabolic collector, and this is a tube, and this is a tube. Two is a actual tube and metallic tube, and one is a transparent glass tube. This is a concentric tube. So we are taking here front side view. Now it is a front view of the collector. So it will look like this, and this tube length will be along the length of the collector, and this one is a width. You see, this is a width of the collector. The length is not visible here. This is a width of the collector. And you see here shadow area D naught. This is a shadow area D naught along the length, along the whole of the length. This shadow will fall along the whole of the length, and radiation will come like this. Radiations will come like this. A direct beam radiation, and focusing here. Focus will be on the concentric tube. Concentric tube. This will be concentric tube like this. This is the way how radiation incident and focus on the concentric tube. And from concentric tube it will reach to the collector tube. Means this is observer surface. This is the observer surface. So take a cut section of this observer tube. Take a length, and this is the concentric tube. This is a concentric tube. Here temperature is Tc, and here temperature is Tp, and fluid will flow along this. Take a small strip dx. Thickness of this tube dx. And here fluid convective heat transfer coefficient of fluid is HF. Temperature at this is position X. Temperature is here TF, and here temperature equal to TF plus DTF. From here position is X, and somewhere position will be X equal 0, and because we have taken a very small dx thickness. So let us calculate how to, and this diagram we will take as a reference for calculation purpose. So how much incident radiation coming on this surface reaching to the observer surface, that is thickness dx. Up to df thickness, how much radiation coming on the collector surface are reflected and reaching to the observer surface. So rate of heat gain by the observer tube. We want to find out rate of heat gain by the observer tube. dqu is a rate of the heat gain. Whole thing we will take in bracket because we know that dx is common, so dx will be taken out common, and radiation, that direct beam radiation is IB. IB is a direct beam radiation. Because only direct beam radiation will be focused on the will be reflected by the collector surface. Otherwise, diffuse radiation cannot be reflected from the collector surface to the observer. So IB and RB is tilt factor, and equal to cos theta upon cos theta z. If is a tilt factor. So IB, RB, because radiations are not coming normal, always normal, but some tilting from the normal. That's why we are including here tilt factor RB. Cos theta upon cos theta z. Cos theta is incident angle of the radiation from the normal to the surface, and theta z is a zenith angle that we have discussed during flat plate selector and solar radiation geometry. IBRB and this tau alpha b, product of the transmissivity absorptivity for the observer and collector combination. Observer and collector. For observer and collector, tau alpha b is a product of transmissivity and absorptivity. And next, reflectivity. Because 100% is not reflected, then intersecting factor, because 100% is not intersected by the collector surface, then area W minus D naught effective width of the surface, and length We have taken only dx, so dx we will take common for all, and plus this is a radiation reflected from the surface, but direct beam radiation also coming on the surface. Some direct radiation also coming on the surface of the tube. Direct radiation which directly reaching but not reaching to the collector. These are direct beam radiation coming on the tube, not from the reflected from the surface. So it is also there IB, because it is direct, so it is IB only, not RB. IB, and some tilting, here tilting is not there because it is direct beam radiation IB, and IB RB we can take some radiation will be tilted also, so IB RB. And then area is always, because only on diameter D naught direct beam radiation coming, not pi D naught, only on upper surface of the tube, that is a D naught only, D naught, and dx is area. So D naught and dx is the area of this tube, and dx we will take common, and this is a total radiation coming from reflected from the collector and direct beam radiation IB RB D naught, and plus and minus some losses will be there from the tube, and losses can be defined as pi D naught, pi D naught into UL, overall loss coefficient, because losses will be from the radiation, convection and conduction, all, so that is UL, overall loss coefficient. And because losses are occurring because plate temperature Tp minus ambient temperature, surrounding temperature Ta, and now whole is multiplied by dx, because dx into d naught, dx into w minus d naught is the area of the concerned surfaces. One thing that we will take common here, w minus d naught, to make this equation simplified one. So take common IB, RB, tau, alpha b, rho, gamma intercepting factor plus IB, RB, d naught upon w minus d naught and minus pi d naught ul upon w minus d naught T minus Ta bracket w minus d naught into dx. So here one factor you can see here, this is only intensity. You see that this is equivalent to effective intensity of solar radiation reaching to the observer surface. This is equivalent of, because you know that IB RB is a intensity, RB is a dimensionless, tau alpha is dimensionless, rho is dimensionless, gamma intercept is dimensionless, IB RB again dimensionless, d naught upon w minus d naught is dimensionless. So whole thing is equivalent to intensity, that is a so effective solar intensity of the combined observer and this collector surface. So simply we replace it by S, and you know this one. You know this one is a concentrating ratio. Concentration ratio already we have defined CR equal to W minus D naught upon pi D naught. Already we have defined it in previous lecture. So this is a concentration ratio. So this equation becomes very simple. That is equal to S minus UL by C bracket TP minus TA into W minus D naught into dx. This is equation number 1. So this equation becomes very simple. S is the effective intensity, UL is the overall loss coefficient, C is the concentration ratio, TP is a collector observer tube temperature, T is a ambient temperature, W is a width of the collector, T naught is a diameter of the outer surface of the observer surface, dx is a small element that we have taken for the analysis, dx. So this is a very simple equation, and we write here, after removing this one, final equation we write here, dqu useful heat gain rate equal to S minus UL by C TP minus TA into W minus D naught into dx. This is equation number 1. This is equation number 1. Removing all other things, there is no need of this now. Already we have defined it. So now this radiation, this useful heat gained by can be defined by another way. So how much because we know that heat is coming from TP, heat is coming from the observer tube temperature to the moving fluid, from here to moving fluid. So and that way we can also define a useful heat gain by the fluid. How much the fluid is taking a useful heat gain from the uh, collector. That can be also defined as dQu equal to HF pi di internal diameter, because from this tube to this diameter is कितना है, diameter is here di, and here diameter is d naught, so from this diameter is di, internal diameter of the tube is di, out diameter is concentric tube diameter is d or do. So pi di into dx area into HF. Simple equation, you know that Q equal to H area A delta T. This equation I am using here. Convective heat transfer coefficient, because by convection fluid is gaining heat from the tube by using convection only. So convection is the dominant mode. Most of the energy fluid is taking due to convection. So pi di dx HF into TP minus TP minus TF. Equation number 2. And equation number 3. Again we can define this one, because we can measure by now experimental method, because we know that what is the rate of mass flow. So another equation will be there, dQu equal to M. It's the rate of mass flow, because we can measure how much temperature gain is occurring in the fluid. And actually we can measure inlet temperature and outlet temperature. M Cp is a specific heat of the transporting fluid, that is synthetic air or some other fluid, Cp, and then Tf plus dTf minus Tf. Tf is a inlet temperature at this point at x plus dx. Temperature become Tf plus TTF. So you will remove this one. So it will become M Cp TTF. These are three equations, and all three equations will be used for the finding out for collector efficiency factor and collector heat removal factor. Now taking equation 1 and 2. Taking equations 1 and 2. We know that both are same. Left hand side are same, so right hand side are same. By using these two equations and after manipulation and calculation, we equate one and we can eliminate Tp in terms of Tf. Only purpose of using this equation, Tp is a variable temperature and Tf is a measurable temperature. So here it will be easy to replace Tp by Tf. By using equation number 1 and 2, and we will get equation dQu equal to f dash s minus ul by c Tf minus Ta into W minus D naught into dx. Equation number 4. Here f dash is a collector efficiency factor. This f dash is 1 upon ul plus do upon di into 1 upon HF. So if collector factor f dash is this one, then this equation become dQ equal to f dash s minus ul by c Tf minus Ta minus into W minus D naught into X. So simply you can see collector efficiency factor f dash. How we can define collector efficiency factor f dash by using this equation? So let us see how we can define collector efficiency factor by using this equation. So let us see writing equation. Only this equation we will write here, and other equation we will remove. No, because these equation will not be used. Only this equation we have to consider. dQu equal to f dash and s minus ul by c and Tf minus Ta into W minus D naught into dx. Equation number 4. That is for our concern. So how we define a collector efficiency factor by using this equation? Already by mathematically we have defined this one. This is a collector efficiency factor. But from here how क्वालिटेटिव मतलब सब्जेक्टिव वे में कैसे डिफाइन करेंगे? तो फार्मूला हो गया इसका कलेक्टर एफिशिएंसी फैक्टर जो कंसंट्रेटिंग कलेक्टर जो सिलेंड्रिकल कंसंट्रेटिंग कलेक्टर है उसका फार्मूला ये हो गया. बट क्वालिटेटिव डिफाइन करने के लिए क्या करोगे? यहां से देखिए यू कैन राइट डी क्यू यू बाई डी एक्स अपॉन एस माइनस यू एल बाई सी टी एफ माइनस टी ए W minus D naught. So simply equal to F dash. So rate of heat gain per unit length. F dash equal to ratio of rate of useful heat gain per unit length. Because हमने इसको डिवाइड कर दिया dx. क्या बन गया ये? Rate of heat gain, useful heat gain per unit length to the rate of heat gain per unit length when collector observer plate temperature equal to collector fluid inlet temperature. This is a concept of defining F dash collector efficiency factor. Means once again, it is a ratio of rate of useful heat gain per unit length to the useful heat gain per unit length when collector observer plate temperature become collector fluid inlet temperature. So this is always maximum possible value collector efficiency factor. So this is maximum, this is ideal, and this is actual. This is actual, this is ideal. Actual upon ideal is a collector efficiency factor. So this parameter is useful in defining performance of. These are very important factors. Another factor that we are going to define is a collector heat removal factor. So this is also very important. Once the temperature of the collector observer plate equal to collector fluid temperature, maximum possible efficiency is there. Maximum possible efficiency is there. This is not more than this one. इससे कम नहीं हो सकता टेम्परेचर, टीएफ से कम नहीं हो सकता है. जो प्लेट टेम्परेचर होगा और टीएफ जो बराबर हो जाएंगे तो हीट आना बंद हो जाएगा वहां से. मतलब देयर इज नो एनी ट्रांसफर ऑफ हीट फ्रॉम द ऑब्जर्वर ट्यूब टू द मैक्सिमम ट्रांसफर हो चुका है क्योंकि फ्लूइड टेम्परेचर और जो है प्लेट कलेक्टर ऑब्जर्वर ट्यूब टेम्परेचर दोनों बराबर हो चुके हैं. तो अब कन्वेक्शन कंडक्शन कुछ भी नहीं होगा, तो मैक्सिमम एफिशिएंसी आपको मिलेगी उस कंडीशन में. ये हमारा हो गया कलेक्टर एफिशिएंसी फैक्टर. Another factor we are going to define is the collector heat removal factor by using equation 2 and 3. जो हमने इक्वेशन यूज किया था उसको लेके हम ये इक्वेशन एक इक्वेशन और था उसको यूज करेंगे. तो ये हमने डिफाइन कर दिया. लेट अस नाउ रिमूव इट. अनदर इक्वेशन में जो डिफाइन किया था डी क्यू यू इक्वल टू एम सी पी एंड डी टी एफ. इक्वेशन नंबर जो था हमारा 3 था 3. तो 3 and 4 को ले लेते हैं, दोनों बराबर है. लेफ्ट हैंड साइड तो राइट हैंड साइड को बराबर कर दीजिए एंड देन कैलकुलेट करते हैं इसको. नाउ इक्वेटिंग इक्वेशन नंबर 3 and 4. लेफ्ट साइड है बराबर है डी क्यू यू एंड राइट साइड को बराबर कर देते हैं. तो एम सी पी डी टी एफ इक्वल टू एफ डैश एस माइनस यू एल बाई सी टी एफ माइनस टी ए डब्ल्यू माइनस डी नॉट इंटू डी एक्स. दोनों बराबर हो गए. अब हम इसको इंटीग्रेटेबल फॉर्म में लाने के लिए हम यूएल बाई सी को हम कॉमन करते हैं, बाहर निकाल लेते हैं. एफ डैश यू एल बाई सी टेक कॉमन. सो इक्वेशन यू विल फाइंड हियर सी एस अपॉन यू एल, सी एस अपॉन यू एल. अब इस ब्रैकेट को नाउ ओपन इट सो इट विल कम आउट टी ए माइनस टी एफ. नाउ ब्रैकेट ओपन क्लोज करते हैं W minus D naught into dx. अब ये this quantity will take left side and this quantity we will take right side. So DTF upon CS upon UL plus TA minus TF bracket equal to F dash UL upon C m डॉट सी पी. नो m डॉट सी पी ये गलत हो रहा है थोड़ा सा. सी एंड m डॉट सी पी एंड w माइनस डी नॉट इंटू डी एक्स. फर्दर इसको हम सी जो हमारा कंसंट्रेशन रेशियो है इसको हम डिफाइन कर लेते हैं. कंसंट्रेशन रेशियो को वैल्यू रख देंगे तो पाई डी नॉट नीचे आ जाएगा एंड डब्ल्यू माइनस डी नॉट कट जाएगा। तो इसको हम ओपन करते हैं, एफ डैश यू एल डब्ल्यू माइनस डी नॉट इंटू डी एक्स एंड पुटिंग वैल्यू ऑफ सी डब्ल्यू माइनस डी नॉट अपॉन pi d naught into m cp. So w minus d naught removed and equation pi d naught will go up, pi d naught ऊपर जाएगा। तो इसको थोड़ा सा हम यहाँ से हटा रहे हैं, no need of this one. तो equation simply will reduce dtf upon cs upon ul plus ta minus tf, sorry, TF equal to pi d naught f dash UL into dx upon m dot cp. This is equation number, you can say 4 तक हम चले गए थे, 4 this is equation number 5. Now this equation is integratable. Integrate this equation. So integrating this equation, इसको हम कर देते हैं integrate. So what will get after integration? You see minus ln cs upon ul plus ta minus tf. Minus sign is because here you can see minus equal to pi d naught f dash ul x upon m dot cp into एक कांस्टेंट आ गया यहाँ पर। कांस्टेंट को हम डिफाइन करते हैं केस, बिकॉज ऑलरेडी वी हैव टेकन सी द कंसंट्रेशन रेशियो, so no need of defining constant by c. So this is the question number 6. So how we get value of constant here? By putting boundary condition here. Now applying boundary conditions, apply boundary conditions. First boundary condition is x equal to 0, tf equal to tfi. Add in x equal to 0 कहाँ पर होगा? Where x equal to 0 means at the entrance, at entry of the fluid, जहाँ से ट्यूब का entrance हो रहा है, from where tube is starting and fluid is entering from the tube. So at x equal to 0, tf means fluid temperature here, tf equal to tfi, fluid inlet temperature. Tfi means the fluid inlet temperature. So here you will see minus ln cs upon ul plus ta minus tfi equal to k, constant. So putting, now we get constant and put value of constant in equation. So putting value of constant in equation, we get equation like this, minus here minus ln cs upon ul plus ta minus tf equal to pi d naught f dash ul x upon m dot cp and plus, here sign is minus, sign because k is minus में आ रहा है, तो ln cs upon ul and plus ta minus tfi. So this value you transfer in left side and take a common of the whole log and you will get equation. Now remove this one. So equation will be like this, ln cs upon ul plus ta minus tfi upon cs upon ul plus ta minus tf. This is equation equal to right side pi d naught f dash ul x upon m dot cp. This is equation. Now taking anti-log of this equation, equation number 6, taking anti-log of this equation. Now take anti-log of these equations. So what will happen? cs upon ul plus ta minus tfi upon cs upon ul plus ta minus tf equal to exponential value pi d naught f dash ul x upon m dot cp. This value you will get. If we reverse this one, now numerator is coming to this point and denominator will take up. So now reversing this value, numerator to denominator, denominator to nominator. So what will happen? Let us see. Cs by ul plus ta minus t upon Cs upon ul plus ta minus tfi equal to exponential value. Now sign become minus. When you reverse this one also, sign become minus pi d naught f dash ul upon m dot cp into x. So this is a expression for temperature distribution. This is expression for temperature distribution ratio. And now applying another boundary condition. Applying another boundary condition. Take next boundary condition. Apply BC means x equal to L. जब x means hold. Earlier we have taken x equal to 0. Now we are taking x equal to L means at another end of the tube. Another end of tube. From here to here. Up TF, temperature, fluid inlet temperature, TF become TFO. Fluid outlet temperature. TFO means fluid outlet temperature. Means when a fluid is leaving from the tube. Earlier fluid inlet temperature, fluid is entering to the tube, and a TFO, fluid is leaving from the tube. So TFO. So here putting value this one. CS upon UL plus TA minus TFO upon Cs upon ul plus Ta minus Tfi equal to exponential value minus sign minus pi d naught f dash ul upon m dot cp x. M dot cp. We have taken x equal to L, so putting here L. X equal to already taken L. So one thing another, just we have to arrange this equation. Nothing we are doing here. Just subtracting both values, left side and right side from 1. Subtracting both values from 1, nothing will happen because either we are adding 1 in both sides or subtracting 1 both sides. So 1 minus Cs upon ul plus Ta minus Tfo upon Cs upon ul plus Ta minus Tfi equal to 1 minus exponential ब्रैकेट में माइनस पाई डी नॉट एफ डैश यू एल एल अपॉन m dot cp bracket close. So here balancing this one we get, now we get here using another color TFO minus TFI upon CS upon UL plus TA minus TFI equal to 1 minus exponential bracket minus pi d naught f dash ul l upon m dot cp. This is the equation, and we know 1 minus exponential. So let us do another work. इसको हम ऊपर ले जाएंगे. Simply we can find out TFO minus TFI. TFO minus TFI equal to, take this value another side, right side, CS upon UL plus TA minus TFI and in bracket 1 minus exponential minus pi d naught f dash UL L upon m dot cp ब्रैकेट क्लोज. एंड इसको और सिंप्लीफाई कर सकते हैं हम अभी स्टैंडर्ड फॉर्म में लाने के लिए. वी आर डूइंग ऑल दिस थिंग जस्ट टू ब्रिंग इक्वेशन इन स्टैंडर्ड फॉर्म. So take C upon UL common. From this equation take C upon UL common, that is equal to C upon UL common. UL means L is only suffix. UL stands for overall loss coefficient. It is not multiplication of U and small l. It is a UL. Suffix L is, so here we get equation S minus and taking bracket UL because taking common, so U will come up UL by C here like this, and TFI minus TA. This equation will be like 1 take C upon UL common, and then in another bracket 1 minus exponential and minus pi d naught f dash UL into L upon m dot Cp. And this bracket close and this one close. And now find out overall useful heat gain. Total useful heat gain क्या होगा? What is total useful heat gain? QU equal, because by using experimental value, because that we can actually find QU. What is useful heat gain? We know mass flow rate M, and we know Cp, and T outlet TFO minus TFI. This temperature we can measure, and mass flow rate, this is general equation using first law thermodynamics calorimeter. So already we have calculated TFO minus TFI, putting this value in this here. So you get m dot Cp, taking value from here, TFO m dot Cp, and TFO, value of TFO by TF minus TFI, that is a C upon UL, and here in bracket S minus UL by C, TFI minus TA, and bracket here 1 minus exponential and minus pi d naught f dash UL L upon m dot Cp, bracket close. So now once again, now putting value of C here, let us put value of C. So putting value of C, W minus d naught upon pi d naught, m dot Cp W minus d naught upon pi d naught UL, and in bracket S minus UL by C, TFI minus TA, another bracket 1 minus exponential minus pi d naught f dash UL by m dot Cp. One thing that we have to do, multiplying here by L denominator and denominator by L. So in another equation, let us erase this one, no need of this. In this equation, we multiply by L denominator and denominator. So equation will become QU useful heat gain equal to m dot Cp W minus d naught into L upon pi d naught UL into L, and in bracket S minus UL by C, TFI minus TA, and in bracket another bracket 1 minus exponential here minus pi d naught UL f dash L upon m dot Cp. So again, I think there is overlapping, so again I am writing here this equation, and so that all terms you can see easily. M dot Cp W minus d naught into L upon pi d naught UL into L, here in bracket S minus UL by C, TFI minus TA, and 1 minus exponential in bracket minus f dash pi d naught UL into L upon m dot Cp. So now you see whole equation visible. So here now what we'll do for further simplifying, defining heat removal factor. Now we define heat removal factor, and you can find it easy to understand here. You will also find easy to understand. So take this value, take this value equal to FR, heat removal factor. This is a heat removal factor. Now say m dot Cp here, m dot Cp here, pi d naught UL, pi d naught UL. You will find easy to understand how to understand this equation. So Fr is a heat removal factor. So now this equation become very simple. This equation become very simple, and this equation become very simple. Q equal to Fr, heat removal factor Fr, and W minus d naught into L, that is a, this value is a area, and simple equation become S minus UL by C TFI minus TA. This is a useful heat gain of the concentrating collector. Useful heat gain कौन कर रहा है? Which element is taking a useful heat gain? Means fluid. How much fluid is taking energy? That is a useful heat gain, FR. And now FR you have defined here. FR we have defined here. FR equal to M dot Cp upon pi d naught UL into L, and in bracket 1 minus exponential minus f dash pi d naught. This value you can put here, pi d naught UL L, and this value you put here upon M dot Cp. So now you find easy to understand how this equation. Fr is a heat removal factor. It is a dimensionless number. Heat removal factor is a dimensionless number. That is a heat removal factor, and this equation of useful heat can become very simple. Heat removal factor become very simple. So how we define now heat removal factor? By using this equation. So now removing this one, and now writing overall this equation. QU equal to FR, heat removal factor, W minus D naught into L, this is area, and S minus UL by C TF5 minus TA. So heat removal factor already we have defined by formula. So QU upon W minus D naught into L, area, and S minus UL by C TFI minus TA. Now see here. It is ratio of useful heat gain. Heat removal factor is a ratio of useful heat gain to useful heat gain when collector fluid temperature become fluid inlet temperature. Means TFI minus T fluid inlet collector plate temperature. मतलब collector का जो temperature है become fluid inlet temperature. Maximum possible heat transfer will occur when collector observer tube temperature Tp become equal to TFI, means fluid inlet temperature. Then no further heat transfer will take place. This is maximum possible heat transfer that can take place from the collector observer tube surface to the fluid. So this is maximum possible heat. This is minimum temperature up to which collector can operate. Means a collector fluid temperature become collector fluid inlet temperature, which is equal to collector observer tube temperature. So this is a ratio of useful heat gain. Ratio of useful heat gain to the useful heat gain when collector observer tube temperature become collector fluid inlet temperature. Collector fluid inlet temperature. This is a fractional value. Fr is always less than 1 because this is always greater than this one. So this value is always less than 1. So this is a parameter by which we can define what is a collector heat removal factor. Means maximum the collector heat removal factor, maximum will be collector performance. Maximum will be collector performance. So these are cardinal parameters on the basis of which we pursue research to improve this value FR. And FR improve करने के लिए overall loss coefficient we have to reduce. Overall loss coefficient when reduced collector, and overall loss factor can be reduced when TFI is reduced, and this is maximum possible minimum temperature of TF, fluid inlet temperature. So these are ways by which we can further improve the collector, concentrating collector, any kind of collector. These two parameters, collector efficiency factor and collector heat removal factor, are very important. Without these two factors, we can not further improve the collector performance. So that is why we have discussed, though lengthy, but once you go through and understand things, you will find yourself that it is really a matter that is very useful for us. We have something learned that is a qualitative way, and we go inside. हम काफी अंदर तक जाके चीजों को समझ पा रहे हैं. यहाँ पर कलेक्टर के हम परफॉर्मेंस को, it is a level of the at which engineer has to work and provide solution by further improving the collector performance. So now again we have to define collector thermal efficiency. How? Now we get a useful heat gain. So how we define collector thermal efficiency? Ni, efficiency of the collector. Useful heat gain, already we know. Qu upon what is the total energy incident on the surface? Well, useful heat gain upon total energy incident on surface. IB प्लस मान लेते हैं कि डिफ्यूज भी ले रहा है IDRD, IDRD मतलब सरफेस से रिफ्लेक्ट होके पहुंच रहा है. आईडी सरफेस इज वेरी वेरी मतलब स्मूथ है एंड पॉलिश सरफेस है एंड रिफ्लेक्टिंग इट डायरेक्टली टू द कलेक्टर सरफेस एंड इट अगेन रिफ्लेक्ट इट बैक टू द ऑब्जर्वर ट्यूब और बैक टू द सीधे ऑब्जर्वर ट्यूब. तो यहाँ से रिफ्लेक्ट डिफ्यूज होके आ रहा है, सीधे कहाँ पर जा रहा है? ना यहाँ पर नहीं जा रहा है, यहाँ से डिफ्यूज होकर सीधे जा रहा है ऑब्जर्वर ट्यूब में जा रहा है. तो दैट विल बी टेकन बाय द ऑब्जर्वर ट्यूब मल्टीप्लाइड बाय कितना एरिया इसका है? W इंटू एल. टोटल लेंथ कितनी है? एल है और W क्या है? इसका विड्थ है. नॉट टेकिंग W माइनस डी नॉट बट W L. तो अगर हम इसको, दिस फैक्टर इज ऑलवेज वेरी वेरी स्मॉल, वी कैन रिड्यूस, वी कैन नेग्लेक्ट दिस वन, दिस कैन बी नेग्लेक्टेड because it is always very insignificant compared to IVRB for the big collector. जो कलेक्टर बहुत बड़े होते हैं उसके लिए ये IDRD जो डिफ्यूज रेडिएशन होता है बहुत छोटा होता है कंपेयर टू IVRB जो डायरेक्ट बीम रेडिएशन होता है उसकी तुलना बहुत कम होता है. तो इक्वेशन बिकम वेरी सिंपल अगेन. दिस इक्वेशन बिकम वेरी सिंपल. Ni thermal efficiency equal to Qu upon IBRB into W into D naught. So this is a collector efficiency, thermal efficiency, and all about collector heat mole factor and collector efficiency factor. I think you will enjoy. You have to do 2 to 3 times practice of how to integrate, how to assume values. So actually once you go to derive this equation by your own, you will find yourself missing some information. So see it again, and once you become perfect in deriving this equation and understanding all basic parameters, then you will enjoy how collector works. Thank you very much for today's discussion. I hope you will like and please share to your friends and make comment on any topic that you want to get a video lecture. Thank you very much and have a nice day.